I have to turn on the microphone. Okay, first, I would like to thank you very much, the Federal President, the President of Humboldt University, for this opportunity to be here, to talk with you, with the two, I think, very critically important scientific issues we are facing today. One of them is the scientific challenges of global climate change, and the other one is, of course, what will happen with the Amazonian forest. That is a critical piece of the Earth system that keeps the climate as we know right now. So basically, first, when I was reading Humboldt work in the last few weeks, several things come up to my mind. Okay, the first one, that his view of the cosmos has a really nice unifying perspective of the studies of natural science and mankind. So basically at that time, this was very much integrated, and it's very hard to do that in the university as we have the university today. But the most important thing is actually that Humboldt suggests that you have to contemplate the beauty of the cosmos to obtain a personal inspiration and a beneficial awareness about life. So this makes the science very different from the science we do on a day-by-day basis, I think, you know. So I will try to follow this kind of philosophy. So the story I will start to tell you, it's a very long story, actually 4.5 billion years ago, when actually our planet started to be formed. Well, after a very, very long evolution, you know, the evolution of life and geology in our planet always came together exactly as Humboldt has worked with it, you know. But just for you to have an important point is that we as a species just showed up in this history only 200,000 years ago. So it's a very, very, very short time in 4.6 billion years. So humans are present in the history of our planet just on the very last second. And that's an important thing to have in mind, you know, because you need to take care of the planet and the other species we share in this planet as best as we can. And you will see that probably we are not doing that very well. So basically, if you look that we are changing the face of our planet very quickly and in many, many different ways. If you look into several of the socio-economic trends, you see in terms of human population, using of natural resources, use of water, aquifers, and so on, you will see that everything goes exponentially. So you don't need to be a statistician to see that this cannot go like that in a planet with limited natural resources. And these pressures are making a lot of different impacts on the planet ecosystem. That goes for instance, surface temperature, ocean acidification, coastal nitrogen, aquaculture, everything is going up also. In a planet with limited natural resources, again, this cannot continue. And the question is, which will be the impacts in our society of all this change? This is probably one of the most important questions we have in science today. And we have to answer this question to our society as scientific community, and also to provide to the policymaker the best alternative on how to deal with these pressuring issues. This was recognized in the scientific community as cover of many of the nature and science issues. I choose this one that basically define that you are entering in the Anthropocene. And they define the Anthropocene as a time when humans and our civilization become a major geophysical planetary force. This is really a very strong statement. So basically, we are taking over one single species. In 4.6 billion years, we are taking care of the whole planet. This was recognized by scientists, but also in terms of economy. This is the cover from The Economist in 2011, Welcome to the Anthropocene. So basically, not just from the scientific point of view, but also, and most important, for the societal point of view, we are taking over the planet. And there are many ways that you can see this. This is a plot from the last Intergovernmental Panel on the Biodiversity that was released a few months ago. So basically, this is how much of the land are you taking over in terms of agriculture, in terms of water resources, and so on. So you're going to see that the human appropriation is very high in Europe, in India, in China, United States, all over the place. So basically, we are taking over 60% of the planetary surface, one single species, us. And then if you look for the amount of wilderness area, there are very few wilderness area in the boreal forest, in the Amazon forest, in the deserts of Sahara and Australia. So basically, only 22% of the total land area is remaining, let's say, as we find out 200,000 years ago. So this has a lot of different impacts, like changing soil organic carbon, that's critical for agriculture, and many other aspects. A group of scientists a few years ago sit together to try to discuss what are the limits that we can go on without really going over critical limits in our planet. That's not an easy task for science. And basically, they identified 9 different boundaries that includes biodiversity, land system change, biogeochemical flows, ocean acidification, and so on. And basically, from the 9 boundaries, 4 of them we have already passed the dangerous limit. It's basically on climate, biodiversity, land use in terms of deforestation, on biogeochemical cycles. We are injecting 3 times more nitrogen than the natural system injects into the forest and land as a whole. So basically, if you see this, we have a problem. And what is the reason for this problem? Many of them. One of them is our use of fossil fuels. So this is from the Industrial Revolution until 2015, CO2 emissions in gigatons of CO2 per year. You will see that you are emitting about 40 gigatons of carbon into the atmosphere per year. And 75 of these 40 gigatons, or 80%, came from actually fossil fuel, and only 10% from land use change right now. But of course, the land use change dominated the emissions until the 40s and 50s, and then fossil fuel started to dominate it completely. So these emissions, if the reservoir is very, very small, because the atmosphere, 80% of the mass of the atmosphere is on the first 15 kilometers. So it's just a very, very, very thin reservoir. So if you inject this huge amount, then the concentration have to increase, and that is really what's happening. So this is the time series of CO2, in this case, CO2 emissions. You see that in 2017, what is still growing in terms of CO2 emission by 2%. So basically, besides all the reports from IPCC over the last 15 years, we are still growing in terms of emissions. And in terms of concentrations of carbon dioxide, that's the main greenhouse gases, it was 280 parts per million before the Industrial Revolution. So now we are about 404 parts per million in 2019. So what happens? What happened with this? Basically, our species is changing the atmospheric composition. That is the important point behind the global climate change. And this happens not just for CO2, but also for methane and several other trace gases. So what are the consequences of this change, of this property that one single species in the planet got to do, changing the atmospheric composition? So Arrhenius, in 1896, already published a paper showing that if you double CO2 concentration, the increase in temperature would be about 5 degrees centigrade. So basically, look, more than 100 years ago, before quantum mechanics was established, before you have any computer to do this calculation, Arrhenius shows that, okay, this is not new science. If you double the CO2 concentration, temperature increases by 5 degrees. And he have done just in a ruler, all the calculations. So it's really impressive what these guys have done at that time, including Humboldt, Arrhenius, and other ones. And this new also was not just limited in the scientific community. This is a newspaper report showing that we are adding, at that time, 7 billion tons of carbon dioxide to the atmosphere, and this tended to make the air a more effective blanket to our planet, and will heat up the planet. So, scientifically, and also for the general public, we know this for more than 100 years. So, what we are really changing, what is really the important change, is not the CO2 concentration. But it's important to understand that the most important change we are doing for our planet is change what we call the radiative balance of the planet. So basically, we depend 100% of the sunlight that illuminates our planet. We receive 340.2 watts per square meter every single day. Part of this is reflected by clouds, part is reflected by the atmosphere, and part is absorbed by the biosphere. We use that energy and send back to the space a degraded form of energy, that is heat, that is trapped by clouds, by aerosols, and by greenhouse gases. So basically what we are doing is increasing these feedback loops with a lot of different consequences for our planet that you're going to see in a few minutes. So right now, in terms of sources and sinks of CO2 into the atmosphere, 91% of the CO2 is being emitted to the burning of fossil fuel, 90% in terms of, is emitted in terms of tropical deforestation. This number was 18% 7-8 years ago. So we were able to reduce the tropical deforestation from 18% to 9%. It's possible to decrease it even more. We will discuss that later. From all this CO2 injected in the atmosphere, basically 25% is absorbed by the oceans, 31% is absorbed by our forest, and 44% remains into the atmosphere. So you see that 1/3 of all emitted CO2 is being absorbed by forests. And forests are one of the critical elements in our climate system. If you look to this movie, you see that, for instance, this is how forest absorbs or emits carbon into the atmosphere. So we live in a live planet, so dominated by the biosphere. So basically you see that in the boreal forest, spring, summer, winter, as you go on, you see that the amount of carbon stored in the ecosystem. But look what happens with Amazonia and parts of Africa. It's the only place where we have this carbon stored permanently. Summer, winter, spring, and so on. So this shows that, this is a critically important part of the carbon balance in our world. If you look now to the global distribution of CO2, these movies shows with the higher concentrations, more to the red or to the strong yellow, you see that most of the emissions are in the northern hemisphere, where most of the people in our planet lives. So you see much lower concentration in the southern hemisphere. And you also see emissions from biomass burning from South America, from Africa, and also from Indonesia. And you see that the atmosphere is shared by everybody. Every molecule of air that you is breathing right now was already breathed in Greenland, in Brazil, in Asia, in Japan, or whatever, thousands of times. So it's a very precious natural resource that we should not waste. So if you look now in terms of energy, this is energy in our planet. So basically day and night, as the planet rotates around the sun. So basically what you can learn here is that tropical regions are critical for the energy balance in the planet. So they receive about 70 to 8% of the energy that is redistributed to temperate regions all over the world. So any change in tropical regions are critically important for the global energy balance. Another important point is water vapor, because water vapor has two important roles in the climate system. First is the most important greenhouse gas. 70% of the energy in the atmosphere is retained by water vapor molecules, a very efficient greenhouse gas, and is also important because it drives the hydrological cycle. So, and you see, for instance, that if you have here, you see water vapor coming from the tropical Atlantic, being processed in Amazonia and redistributed to the temperate regions. Again, the tropics are critical for the water balance point of view. So if Arrhenius is correct, and if the CO2 concentration is increasing, the temperature must be, if the physics works, temperature must be increasing. And actually, if you plot the average global temperature from the beginning, the end of the Industrial Revolution to 2016, basically our planet have heating up by 1.1 to 1.2 degrees. So that could look a small amount, but actually you see that this has huge impacts in the functioning of the planet. Another important point, this average 1.1 or 1.2 degrees is very inhomogeneous in the planet. So if you look, this is from the IPCC latest report that shows that continental areas heats up much more than oceanic areas. Why? Because water has a huge heat capacity, much larger than terrestrial ecosystem, and of course it's much more difficult to heat up 1 liter of water than the same volume in the terrestrial ecosystems. So you see that parts of the Brazilian Northeast already heated up by 2.2 to 2.5 degrees. So now you see that this is already some significant heating. And you see that in the Arctic, parts of the Arctic already observed heating more than 3 degrees. So when you see the IPCC talking about 1.5 degrees in average, this means 2 to 2.5 degrees in continental areas. And of course, there is a lot of differences in terms of seasonality, summer or winter. So basically, the main message here is that the temperature increase is much higher over land, that already is at 1.5 degrees, than over the ocean. And that's where we live. But the ocean is extremely important in terms of heat balance in the planet. And if the atmosphere is heating up and the ocean is in contact with the atmosphere, the ocean also have to be warmed up. And this is observed. This is trends in ocean temperature. In this case, from the 60s to 2008, you see that several areas of the ocean already heated up by 1.5 to 2 degrees. And this has a huge impact in the marine life, because it means less oxygen in the water, and that also means more acidity in the ocean water. And also it means increasing sea level. And if you look here, for instance, this is sea level rise from beginning of the Industrial Revolution again to 2010. In average, of course, you need to be careful with this average over the whole planet, ocean already increased by 23 centimeters. And the forecast for future, how much will increase the ocean sea level, basically you can see this. This is a National Geographic simulation based on United States Geological Survey topography. You see that in the future, it's possible that Manaus could be underwater. Asunción can be have a beach, you know, instead of Rio de Janeiro. Of course, Rio de Janeiro, Porto Alegre, just talking on Latin America. But of course, if you look to Europe, you know, Belgium, Netherlands, and Northern Germany, you know, could actually be underwater. This will not happen in 10, 20, or 30 years, but as soon as the process starts, it will be extremely hard to stop the whole process. So basically our species got a characteristic of changing the atmospheric composition, change the radiation balance, and the third possible change, changing the geography of our planet. So this happens in Europe, in the United States, in Africa, and in Southeast Asia. And part of this is already happening, of course. Climate change is not in the future, it's actually in the present. And this can be documented by many, many different ways. These are measurements from the GRACE satellite that measure the amount of water in the continents. So basically you see this trend in amount of water in centimeters per year increasing or decreasing. You see in Brazil, the whole San Francisco basin has almost, is completely dry right now. And we are observing an increase in precipitation over the La Plata basin. And you see a decreasing water availability over the Eastern Mediterranean area that is being very strong and very well documented. Part of these changes are natural cycles, and part of these changes is caused by climate change. The attribution is very difficult to do. So we'll have to do a lot of science in the next few decades, actually, to do a mechanism of attribution much more accurate than we can do right now. But anyway, this is already happening in our planet, but we don't know exactly where and how much. So this is not a process for the future, but also actually is happening now. So IPCC have done calculations on the radiative forcing. So all these changes that we are observing, an increase in 1.1 degrees, is just driven by 1.68 watts per square meter for CO2, and the total anthropogenic forcing is 2.29 watts per square meter. Look how sensitive the climate system is to changes in the radiation balance. Only 2 watts per square meter in 322, if you remember the total number there. So it's very, very sensitive to changes in the radiation balance. The question is, how will be the future climate? That's much more difficult question to answer, as you can imagine. But the IPCC have tried to do that, making an ensemble of many models, including Max Planck Institute model, Potsdam global model, and so on. Basically depend on the emission scenarios, but we could have, in the last decade of this century, a heating of about 7 to 7.5 degrees in the northern latitudes. We could have an increase in temperature in Brazil around 5 degrees, That's a very significant change that will make a huge change in agricultural production and on lifestyle of many of us who lives there. So basically, you see that the changes we are talking about are not just small changes in the style. It's actually something that we really have to take care about. So IPCC a few months ago released the special report on global warming of 1.5 degrees, and trying to answer the UNFCCC question. What should we do to limit the increase in temperature to 1.5 or 2 degrees? Okay, you know what you have to do? So this is the global net CO2 emissions you have to follow to limit the heating for 1.5 degrees. So basically in 2020, we have to decrease CO2 emissions by 5% a year. We have to zero emissions in 2040 and start to have negative emissions after that. So that's a huge task for our society. Basically, remember that you are still, from last year to 2018, we have increased the emission by 2.3%. So have to change this to minus 5% per year. So it's a huge change in the energy and in the society as a whole. And then another question is how to get these negative emissions here. There is only one single process that we know that is efficient in removing CO2 from the atmosphere, and it's called the photosynthesis. That's it. It's the only process that we know that could work on this large scale. We'll get to this point later. And the IPCC put several possible scenarios for how to get it to 1.5 degrees. Without going too much detail, you see that it trusts on agricultural, forest, and other land use, carbon dioxide removal using some kind of geoengineering technique that do not exist yet, and then bioenergy with the carbon capture and storage. So basically, we will have to remove CO2 from the atmosphere at a gigantic scale with lots of science still have to be developed on how we're going to do this at the scale that's necessary at a planetary scale. So, and then came Amazonia. So Amazonia can be part of the solution for this issue we are discussing. It's a very unique region with global impacts on the carbon balance, we will see that, and also on the hydrological cycle. So basically, it's important to get the message that Amazonia is a key component of the Earth's system, but also is suffering a lot of different changes that we're going to discuss here. And one of the points is that recently Carlos Nobre and Thomas Lovejoy published a paper in Science showing that if you get 40% deforestation in Amazonia and 30% less precipitation, we cannot ecologically sustain a tropical forest. So all the forest will be gone because it will not have ecological conditions to sustain this type of carbon in the ecosystem. And this is critically important. So if you look into Amazonia, Amazonia is not just important in terms of carbon. Basically, 15% of the global net primary productivity, that's the amount of carbon fixed in the ecosystem, happens in Amazonia, and it has 120 billion tons of carbon. So it's a small fraction of this carbon goes to the atmosphere, bye-bye to us, because then the increase in temperature will be very, very fast, much faster than if the carbon is stored on the ecosystem. On the other side, if you can enhance the fixation of carbon in this ecosystem, eventually this can, we can have some more time in terms of the effects in terms of climate change. But also, Amazonia is the most powerful hydrological basin in the world. So basically 18% of fresh water in the global oceans came from the Amazon River alone. And the Amazon River discharge is extremely high. So basically the hydrology of Amazonia is extremely important globally. In terms of biodiversity, we have about 10% of all the biodiversity species in our world. In terms of climate stabilization, is a very important heat sources for the atmosphere, with the 2.4 meters average rain in Amazonia. Some of parts of Amazonia, we can have 3.2, 3.4 meters of water every year. And also culturally and ethnically is a very, very diverse region. And if you look here, in terms of global net primary productivity in this map, you see that Amazonia is absolutely critical in terms of carbon balance in the world. So if you're going to plant trees to sequester CO2 from the atmosphere through photosynthesis, where are you going to plant these trees? In tropical areas. That's the only way that it can work on this kind of scales that you want. But Amazonia is also with problems. The first one is deforestation. So this shows deforestation from the 70s until last year. And you see that Brazil was extremely successful in reducing deforestation from 27,000 square kilometers deforested every year to about 4,500 square kilometers per year, 1,000 square kilometers per year. But look what is happening over the last 4 years. It starts to go up again. So basically, what should be going down here until we reach zero, actually right now we are deforesting about 8,000 square kilometers per year in 2018, and probably in 2019 this number could be higher. Another way of looking to deforestation is looking to the fire spots in Amazonia. So basically we see a very important drop in fire spots until 2012, but again you see an increase in the number of fire spots. So you see an increase in terms of biomass burning smoke in Amazonia. And this smoke is of continental scale. This is a MODIS image, a remote sensing image, where you see the fire spots in red and the gigantic cloud of smoke that covers South America in a continental scale. Of course, this has profound influences into the ecosystem. And if you look into the tropical tree cover loss from the last 20 years, you see that's going up worldwide. It's still increasing. And we are the tropical forest in terms of countries. Brazil, because it has the largest 5.5 million square kilometers of forest, but also in Africa and Indonesia. You see that is not just for Brazil or Democratic Republic of Congo. So it's a worldwide issue that we have to establish policies to reduce deforestation. And Amazonia is also critical for the water vapor transport to places in Brazil and Argentina where agricultural fields are located. So basically this water vapor is produced in the tropical Atlantic, is processed in the trees in Amazonia and get to feed the soybean and also cotton and many different cultures here in the southern part of South America. And Amazonia is also changing a lot. So one of the things we are observing is that it's changing the river discharge in the mouth of the Amazon River is increasing by 30% over the last 20 years, for both the wet season and also for the dry season. So actually, what is driven this intensification of the hydrological cycle in Amazonia, possibly the increasing sea surface temperature in the tropical Atlantic. So you see that Amazonia is not an isolated region in the world. but of course it has external forcings that can change dramatically the inner work of the ecosystem per se. Another important change we are observing is the increase in the extremes. So basically this is from the beginning of last century up to the 2015, you see the increase in the maximum level of water level in Manaus, and also a decrease in the minimum level. So actually we are increasing the extremes in terms of climate for Amazonia. And of course, the ecosystem is not adapted to deal with these increasing fluctuations in terms of precipitation, river level, and so on. Another important point is that the dry season length in Amazonia is increased. So if you look into the 80s until the very last day, so the rain starts to come late and late, actually by 3 weeks over the last 20 years. That's a huge change. And what is the consequence of that is that if you have a longer dry season, you have more burning, you have more biomass burning, so this is a negative feedback for the ecosystem. So this worries us a lot. But Amazonia is critically important for the carbon cycle. So basically, if you look into the amount of carbon stored in the tropical intact forest, is a huge amount that is similar to the amount of carbon emitted to the atmosphere by burning of fossil fuel. But this carbon is having also, the carbon allocation is changing in Amazonia. So this is a paper published in 2015 that shows the net flux of carbon for the overall Amazonia. This is the productivity, photosynthesis from Amazonia, and this is tree mortality. So what we're going to see is that Amazonia, 10 years ago, was absorbing about 0.5 tons of carbon per hectare of forest. So the forest was absorbing the excess CO2 from the atmosphere. But starting 3 to 5 years ago, the net carbon flux now becomes 0. Why? Mostly because the tree mortality have a significant increase. Why that? Because of the droughts in 2005 and 2010. So the droughts are changing the ecosystem that is very sensitive to the length of the dry and wet season. To monitor this process, we have some very nice German, Brazilian collaborations. One of them is the Atoll Tower that I think your federal president visited last year, right? So basically, it's 325 meters that you built with the Max Planck Institute in the middle of the forest, just to monitor the total amount of carbon in the ecosystem. Also, trying to understand the radiation balance, ozone impact on the forest, and so on. Another important collaboration that we're having to monitor the Amazonian ecosystem is the experiment that we're calling Café Brazil, that's chemistry of the atmosphere field experiment in Brazil, where we'll bring the G5 from DLR to Brazil to really fly up to 15 kilometers high, how the carbon balance is changing, how the atmospheric chemistry is changing, how does this affect the radiation balance. So this is a critically important collaboration for us to understand the science behind the behavior of the Amazonian ecosystem. So, and one of the questions that we want to answer is this. So right now, basically, we have the forest in equilibrium, in a stable, relatively stable equilibrium. So basically, if we deforested and transform it to savanna in the east, southeast, we can change that equilibrium to a different one and reach a very unstable situation like this. So basically, what governs the transition from this to this is to have 40% of total deforested area. Right now, it's about 18%. And if you have a heating of about 4 degrees, right now, the change in temperature is between 1 to 1.5 degrees. So basically, you are not far away from a tipping point where we could destabilize the tropical forest and transform it to a savanna, releasing 120 gigatons of carbon to the atmosphere. That will really get the greenhouse effect more important. Talking on this tipping points, as we'll call, the Amazonia is one tipping point, one critical issue in terms of global climate change, is how close you are from a tipping point in the climate system. So which are these, what we'll call tipping points? So basically, there are several of them. For instance, West Antarctica ice sheet, if it gets destabilized, we can have a huge increase in sea level. The Amazon rainforest, if you get the Amazon rainforest not sustainable in terms of climate, lots of carbon will be emitted to the atmosphere, changes in the thermohaline circulation, and so on. So there are several feedbacks that could be negative feedbacks to the climate system that could get the changes in the climate system much worse than the normal model that works linearly could indicate. And of course, one of them is the Arctic permafrost with the leakage of methane that is stored for thousands of years in the permafrost into the atmosphere. That could be a huge positive feedback into the climate system that can bring a lot of different effects. Another important point that you associate with climate change is the increase in the intensity and frequency of climate extremes. The latest GEO6 UNEP report, I have a chapter on that, that shows very clear that we get almost 3 times more climate extremes than we had just 30, 40 years ago. Mozambique, a few weeks ago, is one example. The large increase in the intensity and frequency of hurricanes in the tropical Atlantic is other, typhoons in the Pacific, and so on. Why this is happening? If the ocean gets warm, you have more energy, you intensify these strong climate extremes. Another very important point associated with the climate change is how will be our ability to feed 10 billion people in 2050. So FAO and the World Economic Forum are always touch on this issue, and this is the potential impact on food production in a 3 degrees hotter world. So you see that, for instance, in terms of Brazil and in terms of lots of different areas in Africa, we could have yields in between 10 to 30% less than we have today. And we are 7.6 billion people now. We will be 10 billion very soon. So we have to feed these 10 billion people. How are we going to do this with this kind of climate change? That's absolutely unanswered question yet. Another important point is the risk of biological species. So basically, South America are the highest risk in terms of loss of biodiversity, but of course this could be important for Australia, New Zealand, whose climate is also changing very fast, especially precipitation. So basically this will have impact, global impact, that could feedback on our species very, very strongly. So just to finish, then we have to start a discussion, what future do we want? So basically, in these scenarios, what do we want in terms of future for our socioeconomic society? So basically, this is a very complex question, as you can imagine. That will depend on a lot of different societal trends, that will depend on our culture, that will depend on our socioeconomic systems, and so on. And then what we want to decide is, do you want world where you can limit the temperature to 1.5 degrees, or let continue with business as usual and have a world with 4 to 5 degrees increase in temperature. So that's a political decision that you have to do right now, and science have to say which are the ways we have to go there. So basically, there are solutions for this issue. So what we have to do, it's actually quite simple, scientifically, but not politically, of course. Basically, to do more efficient use of energy, increased use of low-carbon technology, improve carbon sinks, including tropical forests, and of course, the most difficult thing is to have a profound lifestyle and behavior changes. Especially if you remember that 600 million of Indians do not have access to electricity. We have about 1 billion people in Africa that do not have the very minimum level of consumption. And they will have that in the next 20 or 30 years. So what are we going to do with this issue? So it's not an easy question. And the World Economic Forum have tried to answer this question. So every year they release the Global Risk Report. This is the Global Risk Report released recently by the World Economic Forum. Look that in terms of probability, the top 5 global risks, 3 of them are related to climate change. 2 of them are related to internet and cyber attacks. So basically, extreme weather events, failure to climate change mitigation and adaptation, natural disaster are the 3 main points that the World Economic Forum puts over the table. And this is not the issue raised by scientists or non-governmental, it's not Greenpeace, it's not NGO, it's actually by economists. And in terms of impacts, of course, from the 5 major impacts, 3 of them is also associated with the climate change. So actually this is recognized by science, but also by the socioeconomic system we have. The United Nations, to deal with this issue, have established the 17 Sustainable Development Goals that every country, Brazil, Germany, and so on, have agreed to transform our world. But the latest IPCC report have done a very interesting analysis that is here on this plot. Which are the mitigation options and relationship with the Sustainable Development Goals? So some of them has positive synergies, but also there are trade-offs, negative synergies. For instance, if you wanted to provide water for all the population in the world, you have to spend a lot of energy to do that. You have to spend natural resources. So this is a trade-off to the mitigation effects that you have to do. So basically you see that the issue is starting to get more complex and more complicated. And we need very good policy to deal with this particular thing. But science and policy are not the only thing that drives our world. Actually, the ethical issues also are important. And the very best issue on ethical issues is this encyclical Laudato Si from Pope Francis that 2 years ago mentioned very clear that I urgently appeal for a new dialogue about how we are shaping the future of our planet. We need a conversation which includes everyone, since the environmental changes we are undergoing and its human roots concern and affect us all. This is not a scientific statement, it's not a political statement, it's a moral and ethical statement. And that brings the thing to a much even more complex table that we have to deal with. Science basically have done his job. So here is the cover of only a few of the reports that scientific agency like GEO6, IP, the Biodiversity Report, the IGAC and SPARC, the Global Warming of 1.5, the American Meteorological Society. So basically, science has done his job. So now is the time to go to the public policies. And the only public policy that is in force right now is the Paris Agreement. But the problem is that if all INDC are fulfilled by all countries, we still will have a warming of about 2.7 to 3 degrees in 2050. So that's a very important point. So the only public policy in force right now is insufficient to deal with the needs of the science and the needs of the population. And we know the difficulties to fulfill this INDC. I will get the example of Brazil. So basically, Brazil has a very strong commitment of reducing by 37% his emission in 2025. It's only 6 years from now, and 43% by 2030. How Brazil is proposing to do that? It's a very long document, but basically zero illegal deforestation at 2030 and compensation of emissions from legal deforestation after that. So, and you saw the history of deforestation. Are Brazil going to fulfill his obligation under the Paris Agreement? It will need to do a lot of effort to do that. Also, Brazil is compromised to restore 12 million hectares of forest until 2030. It's only 18 years from now. That's a huge area. So you need science, you need people, you need money to do that. That's not come up free. So it's not very easy to do. Also, restore, we have a lot of degraded pastures area. So restore 15 millions of hectares and have a participation of 45% renewable energy at 2030. This probably will get it, but the other three ones will require a lot of different efforts. So basically, what I want to call the attention is that governance of the climate change issue is a major issue. So basically, as you all know, United Nations was not, let's say, designed to do this huge task that humanity have right now. So basically, governance is really important. So basically, how the necessary measurements will be implemented and who will drive and controls the implementation of these measures by all individual UN countries. So it is a huge task, and we do not have in place a proper governance system to do that. Last but not least, there is another important point that has implication for the Paris Agreement, implication for how we're going to implement these measures, is that the country who contributed to the least greenhouse gases will be the most impacted by climate change. So we have a really serious issue of inequality here. So how are we going to deal with this important issue? So basically, Madagascar, you saw, was completely devastated recently by the typhoon. His emission is almost negligible, and the country will have to spend billions and billions of dollars to restore the damage for the typhoon that reached the country. And the same for many, many other countries. And now, if you look to how much in average a family in Germany consumption in 1 week, compare that with an Italian family, with an Ecuador family, and with a Chad family. So, if you don't change that, it will be very hard to find a solution that will be acceptable by everybody. So that's a critically important issue that is still not over the table, at least clearly. And the role of science This is science here, this is the economy, this is the society, this is governance, and this is mitigation and adaptation. For us to build this whole building, science is the basis, of course. Without science, without the work of IPCC and thousands of scientists over the last 30 years, we will not be speaking here. But science is not enough. Of course, we have economic issues, societal issues that we have to build up for this house of climate change. And more than that, if you look here, how we're going to work in science, in public policies, and so on, to build, this is the basic needs for the society: water, food, education, resilience, jobs, and so on. And these are the limits for our planet boundaries. How we're going to build a safe and just system from the university, for the humanity, from linking the basic needs to the limits of our planet. So this is a task that the scientific, that you have to deal with as much as possible, and how and that we need very solid science and public policy to build this space that will link the basic needs of the population with the limitation of our planet. And then climate is just one single issue. Our planet is being transformed much more than just climate. And if we need to analyze the climate issue integrated with all the other things that are already going on in the planet, like changes in the consumption and production, decarbonization of the energy, how to provide food, biosphere, and water. 80% of the population in 2050 will be living in cities. How to build sustainable cities? That's not a very trivial issue. How we're going to deal with the digital revolution that are going on right now. And most important, how to look at all these issues in an integrated way. So this is a challenge that the university, that the scientific community, together with the policymakers, have to get. And actually, we cannot fail doing that, because 10 billion people will depend from the solution to this particular problem. So basically, if you want to avoid a warming of 4 to 5 degrees, the message is very clear that there is no other way than to use our natural resources in our planet more efficiently and more intelligently than we are doing right now. And if Humboldt would be with us here, remember the very first transparency, certainly he would make very similar recommendation. So basically you see that 200 years, we did not advance too much in terms of building up sustainability and integrated science to deal with the needs of our planet. So the moment is right now, is not 10, 20 or 30 years from now. It will be too late if it's not too late already. So we have an urgent task to do that now, in science, in society, and in public policies. So, thank you very much for the attention.